Hello everyone, welcome to the recitation week 3. On this occasion, I will be solving 4 problems related to Laplace transform. So 3 problems, we have to find the Laplace transform, and 1 problem we need to solve this differential equation using Laplace transform. And for the first 3, we need to find the Laplace and its region of convergence. What is region of convergence? So it is defined as the domain of f of s such that the integral is finite. Okay, so it is not infinity, this is finite. If this integral is finite, then we say that the Laplace transform exists. Alright, so let's solve the first problem. Problem number 1, we have f of t equals to e to the 4t for t greater than or equal to 0, and we need to find f of s. So let's use the definition. F of s, the Laplace transform of f of t, is integral from 0 to infinity f of t e to the power minus st dt, and then we substitute f of t 0 to infinity into the 4t e to the power minus st dt, integral from 0 to infinity e to the power t 4 minus s dt. Our task is just to solve this integral. Okay, remember that this integral corresponds to t, variable t, so we can treat s as a fixed number, or just any number that is fixed. We just need to integrate this function with respect to t. Okay, so we have 1 over 4 minus s e to the power t 4 minus s from 0 to infinity. Okay, we have 1 over 4 minus s limit t to infinity e to the power t 4 minus s minus limit t to 0 e to the power t times 4 minus s. Okay, so for the first limit, assume that 4 minus s is negative. If 4 minus s is negative, that means s is greater than 4. Then as t goes to infinity, this term should go to 0, right? So we obtain 0 if s is greater than 4. Okay, so we have 1 over 4 minus s, this is 0 by our assumption, and then minus limit t to 0. If t is 0, then e to the power 0, or any number other than 0 to the power 0, is 1. Then you have 1, so it's minus 1 over 4 minus s, or 1 over s minus 4. And the region of convergence is our condition here, s greater than 4. Okay, so that's solution of problem number 1. Problem number 2, we have small f of t equals to t minus 1 or 3 greater than or equal to 0. We need to find the corresponding Laplace transform. Alright, again, so let us apply the definition of Laplace transform. So it is integral from 0 to infinity, and f of t is t minus 1 e to the power minus st dt. Okay, for this particular form of integral, one of the easiest way is to use integration by parts. All right. Okay, so let us assume. Okay, let's review the integral by parts. So integral by parts is integral of u dv equals to uv minus integral of v du. Okay, so somehow we treat this as u, the other is dv, and then we work to find uv and integral of v du. For this, assume u is t minus 1 and dv is e to the power minus st dt. Both give us, so what is du? Du is dt, and phi is the integral of this, right? So integral of e minus st dt, you have minus 1 over s e power minus st. So let's apply integral by parts. If f of s is uv, so 1 minus t over s e to the power minus st from 0 to infinity minus integral v du. We have minus sign there. So, okay, we have plus sign e to the power minus st, and then du is dt. Don't forget the integral sign, 0 to infinity, and then you substitute here again. Assume that if minus s is less than 0, then, or negative, then st goes to infinity. This term is approaching 0. We have 0, then minus, we substitute 0, this term becomes 1, this becomes minus 1 over s, and then plus this integral 1 over s minus 1 over s e to the power minus st infinity 0. We have minus 1 over s minus 1 over s squared. Again, this term here 0 minus 1, so minus minus you have plus, so is it, yes, so it's 1 over s squared minus 1 over s with region of convergence s greater than 0. This is the final solution for number 2. Okay, let's continue. For problem number 3, we have f of t. This is a discontinuous function, 0 t 2, and then it's t minus 2 when t is greater than or equal to 2. We need to find the corresponding Laplace transform. Okay, let's just apply the Laplace transform. 0 to infinity f of t e to the power minus st dt, and then you apply. So from when it's 0, so it's 0 when t is between 0 and 2, and then it's t minus 2 when t is greater than 2. So it is 0, so we can divide the integral sign, right? So 0 to 2, and then 2 to infinity. From 0 to 2, this is 0, so we just need to evaluate the integral for which t is between 2 and infinity, right? So the integral is from 2 to infinity, t minus 2 e to the power minus st dt. Okay, we can solve this using a similar approach as given in problem number 2. Okay, you can use interval by parts. Define u is t minus 2, then du is equal to dt, dv is e minus st dt, then v is, you can look, so it's minus 1 over s e to the power minus st. Okay, and from integration by parts we have uv, so uv 2 minus t over s e to the power minus st from 2 to infinity minus we have plus 2 infinity 1 over s e to the power minus st dt. Okay, again, when assuming minus s is negative or s is positive, then as t goes to infinity, this term goes to 0, we have 0. Then when we substitute 2 there, we have 0, right, because 2 minus 2 is 0, so this term is gone. And then we just need to evaluate this integral. Okay, from the answer from problem number 2 we have minus 1 over s squared e by power minus st from infinity to 2. Again, infinity is 0. When it's 2, then we have e to the power minus 2s over s squared with region of convergence s is positive. So that's the solution. Last problem, number 4, it is a differential equation. We have y prime plus 2y equals 40. Initial condition y0 equals to 3. Okay, so let's use Laplace transform. Y prime plus 2y Laplace transform 40. We need to assume that this holds for t greater than or equal to 0. So the Laplace transform of y prime is as y of s minus y 0 plus 2 y of s, and the Laplace transform of t is 1 over s squared, so 4 over s squared. Okay, and then y0 you have 3, so you have s plus 2 y of s equals to 4 minus 3s squared over s squared, and then you get y of s is s squared s plus 2, this will be positive. Okay, so you have 3s squared plus 4, given that s is not 0, s is not equal to 2. Right, so we need to find the inverse Laplace transform, right? To do that, we need to fraction, like we need to decompose this fraction into several simple terms. So we can have, by using partial fraction expansion, we have a over s plus b over s squared plus c over s plus 2. Okay, so we just need to find these terms abc. So this is a s plus b over s squared plus c over s plus 2, and then you can simplify again, s squared s plus 2. This is a s plus b s plus 2 plus c s squared. Okay, you keep the denominator s squared s plus 2. For the numerator, you can work this out, and it equals to a plus b, sorry, it should be a plus c s squared plus 2a plus bs plus 2b. Okay, sorry, this would be b. So you can compare this y of s here and y of s over here. We have 3 equals to a plus c, 0 equals to 2a plus b, and 4 equals to 2b. From here we get b is 2, and then a is minus 1, and then c is 4. So y of s is minus 1 over s plus 2 over s squared plus 4 over s plus 2. To find the solution, then you can inverse Laplace transform of y of s. So 1 over s is 1 minus 1. 1 over s squared is t, so 2 times t, and then this is plus 4 e to the power minus 2t for t greater than or equal to 0. Okay, so this is the solution of the differential equation. Alright, I hope this quick lecture can helpful for your class, and I'll see you next time. Thank you.